Testing, testing. Very good. You can hear me in the back. Perfect. All right, well, welcome everybody. My name's Jared Atkinson. I'm the Chief Strategist at SpecterOps. Hey, Jeff, how's it going? And I'm going to be talking about purple teaming. Hey. So one of the big questions in the industry, we always use these really abstract concepts, terms like red teaming, terms like adversary simulation, terms like adversary emulation, terms like purple teaming. And the problem is that we all have slightly different definitions. And so one of the ways that I want to start this presentation is by kind of coming up with a synthesized definition where I look at what other people have defined purple teaming as, and then I try to come up with what are the kind of similarities between all those different definitions. So a lot of times what you're going to see is you're going to see some sort of combination of red and blue, right? So there's kind of this, oh, well, red and blue work together, and that's kind of what purple is, right? You're going to see a part about educating students or educating consumers, right? You're going to see something, again, about red and blue teams working together. You're going to understand an organization's ability to detect. You're going to do information sharing. You're going to emulate the adversary for self-evaluation. So you have all these definitions, and here's a couple more, but as we dig into it, we kind of say, what are the features that all of these definitions kind of share, right? And I kind of came up with a couple things. One is collaboration between red and blue, so taking some offensive specialists and working with defensive specialists. Increasing familiarity with or understanding of adversary TTPs, right? Self-evaluation of existing security posture, and improving an organization's security posture. And that involves what I call preventative controls, and preventative controls are focused on stopping the bad guy, so not allowing something to happen. Detective controls, which are alerting on something or kind of signaling that something has happened, but maybe not stopping it. And then response procedures. So a lot of us have been in situations, especially if you're a red teamer, to where your customer, let's say you get a golden ticket, and your customer has some sort of response procedure or playbook where they execute it, and at the end of it, they expect that golden ticket is null and void in some way. And then they execute it, and you find at the end of the day, your golden ticket still works. That would be a situation where a purple team might be able to facilitate the evaluation of that response procedure. Okay? So as we start digging into the different implementations of purple teaming, there's a couple really common ways that people go through it. The first is adversary emulation. And just to kind of give a brief description of what that is, it's essentially where people will use a CTI focus, where they'll look at a known breach and the attack path that was used in that known breach, and they'll try to mimic the steps that the actual adversary used in that breach, right? The benefits are that you get a broad range of attack techniques that are going to be implemented as part of it, and you're simulating a quote-unquote real attack path, something that has actually occurred in reality. But the limitations are that the attack path has to be coherent, right? And so that actually limits your ability. So you're going from point A to point B, and everything that you do has to make sense in the context of that path from point A to point B. And the problem with that is that you tend to only test things in one way, right? And so let's say I want to inject into a process for defense evasion. I'm only going to choose one method of injection. Let's say I want to laterally move. I might use Windows services, but I might not use all the different techniques that you could use for lateral movement. And so what happens is you kind of narrow the scope. And so you test a lot of things, a lot of different techniques or behaviors, but you don't test them very deeply. You don't test all the different variations that exist, okay? And so this brings us to this point of breadth versus depth, right? And the adversary emulation approach, from my perspective, is very much focused on breadth. You'll see people talk about, we test 50 or 100 different attack techniques during this purple team assessment, but the problem is you're testing it in only one way or maybe just a few ways, right? What we really like to think of is the depth aspect of things. So what are all the different ways that somebody could do process injection? If I'm a red teamer and I'm trying to help a defender build and validate their detections or their security controls with regard to process injection, it stands to reason that I should present them with all the various approaches of process injection so that they can know where they're strong, where they're weak. Okay? So here's a simple example. For a long time, there was this real emphasis on attack tools being written in PowerShell. This is the initial kind of living off the land type approach. But as PowerShell tooling became more and more popular, Microsoft actually made a bunch of changes. So they added a bunch of logging, they added some preventative controls with AMC and things like that. And as a result of that, it became relatively dangerous to use PowerShell-based tooling. One of our colleagues, Will Schroeder, he wrote a port of a popular tool called out-mini-dump. So this tool, out-mini-dump, was written by Matt Graber, and what that did was it made a crash dump or a memory dump of lsas.exe, and then could be used with Mimikatz to dump credentials. So out-mini-dump became something that was kind of well-known, easy to detect because of all the PowerShell tooling that had come out. But Will ported that to sharp dump, and sharp dump is a C# implementation of that same code base. And it's very frequent for people to have a detection that would detect something like out-mini-dump, but then as soon as you change the language from PowerShell to C#, that detection no longer works, despite the fact that in the documentation, it says sharp dump is a C# port of PowerSploit's out-mini-dump functionality. He literally looked at the code for out-mini-dump and changed it to C#, and for those that are familiar, C# and PowerShell are based on the same underlying functionalities called the .NET framework. And so the idea that that change was significant enough to evade detection or evade preventative controls, that's not a good thing when we're talking about how well do we perform against this whole class of attacks. Okay? So a second approach, which seems to be the way that the industry tends to go, is using dynamic testing. So you may be familiar with something like Atomic Red Team. Atomic Red Team is an open source tool set or set of test cases where they basically identify, here's the technique, token theft, and then they give you a bunch of test cases that allow you to execute token theft in your environment, right? And then you would evaluate how your controls perform against those different test cases. And the idea is that if you were to catch all of them, then that represents good coverage. If you don't catch them all, then you can kind of identify, why did I catch one but not the other, right? Now, this seems to be a really useful, this is kind of like dynamic analysis when we talk about malware analysis, but we're doing dynamic analysis of security controls in this case. But the problem is that the devil's in the details, right? So which test cases are you presenting in your environment? And that makes a big difference. We did some analysis, and we found that in many of the kind of more common or more open source kind of tooling that does this type of approach, we found that the test cases have a lot of overlap. So there's this question to where when you start to look into the different test cases that you're using, you have to think of the variation that exists within a technique. So in this case, we're looking at process injection. So imagine that there's an infinite number of tools that can be created that would implement process injection, right? Some are going to be more similar to each other than others, and some are going to be more different. They're more novel, you could say. And so one of the questions that we dig into is, generally speaking, you have like what I call a canonical or prototypical tool. And this tool, the best one is, when we talk about dumping credentials from LSAS, what's the prototypical tool? Does anybody have a guess? Mimikatz, exactly. So when you think, the prototypical tool is the tool that pops into your mind when you think about that attack technique. It's kind of the tool that created the category, right? And so that's going to be, let's say it's in the center of the category. Now, the question is when I add my second test case, do I want my test case to be very similar to the prototypical tool? Or do I want it to be very different from the prototypical tool, assuming that I only have 2 test cases? Very different, right? And so the idea is that the more I maximize the difference, the more I could stretch the capability of my detections or my security controls. Okay? And so what we get into is something that starts to look like triangulation, right? There are literally an infinite number of variations or tools that can be created that implement process injection, and we can't test an infinite number of tools, right? That's just not possible. We can't test 1 million tools. But what we could do is we could test a subset of tools, and we can make sure that when we select which tools we build test cases for, we maximize the differences, right? And so we know that we're not just testing the same thing over and over with these very, very small changes. And so this gets into this question of quantity versus quality, right? When we talk about measuring things, we have quantitative metrics, how many test cases you have, and then we have qualitative metrics, which are what is the range of diversity that you're actually presenting in your test cases. And one of the big problems that we have is a lot of these kind of modern approaches to that dynamic testing approach, they use quantity as a proxy for quantity as a proxy for quality. And the problem with that is that assumes that there's a relatively finite number of variations, right? But when we're talking about millions of variations or even an infinite number of variations, 10 test cases is not very much in the face of a million possible variations, right? You might as well have one variation at that point. And so just from a mathematical probability perspective, the likelihood that you accidentally pick the 10 best test cases out of a set of a million is extraordinarily unlikely, right? And so that means that we have to deliberately choose which test cases that we're going to implement to maximize that range of variability. So then the question is, this is what it ends up looking like, right? So a lot of times we did some analysis of some of these open source test cases, and we found that, for instance, there was one open source kind of purple teaming tool. It was looking at credential dumping for LSAS, and they had 12 different test cases, right? 12 sounds like a lot, and it seems like you should be able to do a lot with that. But when we started digging into it, and I'll talk kind of about how we did that digging into, what we found is that 10 of the test cases were just slight variations on Mimikatz. It was the same thing over and over. Maybe they injected it into memory once. Maybe they had a different tool written in C# instead of C++. But it was the same thing over and over and over. And then the other two presented something that was slightly different. And so basically what happened is they were being redundant, and the same test was happening over and over. And so what we want to move into is this question of similarity. And this is where we get into a big problem, right? Because when we think about similarity as far as tooling or attack techniques, we start thinking of things like MD5 hashes or SHA-256 hashes. And so the cool thing about hashing is hashing allows you to identify, are these the same tool, right? So conceptually, if you run one binary, one exe file through a hashing algorithm and it produces a hash, and you run a second binary through that hashing algorithm and it produces the same hash, you can say these are the same tool for all intents and purposes, right? They have the same content. However, what if they have different hashes? Now you can say that they're different, but you don't have the ability to say just how different they are, right? And so imagine that you have one tool where only one byte has been changed, and then you have another tool where there's no bytes in similar with each other. You would say that the one that has no bytes that are similar, you would say that that's more different than the one where there's only one byte that's been changed, right? So then we have this question of, how do we evaluate the degree of similarity as opposed to the absolute nature of similarity? And so what we have to do is start digging into how things work. So to kind of get into this, I have a little bit of a story. I started off my career in the US Air Force, and this is actually a picture of like the ops center that I used to work in. That's not me, but one of the guys that I used to work with. And we were doing an exercise one day, and it was right after golden tickets had first been produced. So like I think golden tickets were discussed at Black Hat in 2014 was the first year. And 2014, like 3 months later, we were at this exercise. And I remember the white cell, the people that are kind of organizing the exercise, they came in and they said, hey, the red team has a golden ticket. What are you going to do about it? And we're like, we're going to find the golden ticket, and we're going to get rid of the red team. And then the white cell left, and we were like, hey, does anybody know what a golden ticket is? Right? And the problem is that golden ticket doesn't actually tell you, that the term golden ticket doesn't tell you anything about the attack technique. Like you can't reverse out what's actually happening on the computer based on the name. And so the idea, the epiphany for me was that if you don't understand something, you can't detect it, right? Or put another way, your ability to detect something is proportionate to your understanding of how it works, right? And so the way that I start digging into this, it's kind of a condensed version of the presentation, so this is going to be a high level, but I'm happy to talk to you afterwards, is we can start to look at a tool. So this is a sample tool. It's a POC. It's meant to be really simple. But what we see here is we see that tools are essentially made of function calls, API function calls. That's how the tool interacts with the operating system. And here we see that there are 4 function calls: open process, virtual alloc ex, write process memory, create remote thread. So this is, if you're a red teamer or you've ever built any red teaming tooling, you would know that this is process injection, right? This is the standard canonical implementation of process injection. And so when we build detections, if I know that these are the functions that are being called, I can start to make decisions about what types of telemetry I might be interested in, right? But the problem is that this is just one version, right? this is written in C, but somebody could rewrite the tool in C# and Go and Rust and all kinds of different languages, and it would be a different tool, but it would still implement this same, I call it a function chain. So it's a chain of functions. Now, what happens if somebody looks into process injection and creates a new function chain or a different function chain? You would start to say that that's more different, right, than just changing the language that it's written in. Now, I like to talk about things a little bit more abstractly than the function call, because there's, for instance, I'll go back real quick. Actually, it's on this page. Let's see. So here we see open process. And open process is kind of the canonical or like the high-level Win32 API function call that you would typically use when you're doing legitimate programming. But there's also like lower-level function calls that do the same thing from the developer's perspective. So an example would be int open process, which is a native API function. Or if you've heard of like direct syscalls, for instance, that would be an example. Well, from a detection perspective, whether the attacker chooses the high-level API function or the direct syscall, in most cases, it doesn't matter, right? So especially now in kind of modern EDRs, it doesn't matter as much. And so what we could do is, instead of worrying about whether they call open process or int open process or write process memory or int write virtual memory, we could just call it the operation, which is process open, memory allocate, process write, thread create. This is just describing what the attacker's doing, okay? And with that in mind, we can start to look at a bunch of different tools. So I'm really into Platonic philosophy, so all of us know the Greek philosopher Plato, I'm sure you've heard of him. He has this idea called the theory of forms. And forms are these abstract categories that things fit into, right? And so you could say that process injection is a form. But then the question is how do you start to define what process injection actually is? And the answer that Plato gave us was that we start to look at the particulars, right? So it's easier for us to say this thing is a dog than it is for us to define what a dog is abstractly, right? And so what we do is we start to look at all the different instances of dogs, all the different particular versions. So I have a dog, Luke has a dog, Kelly has a dog. We all have dogs, and they're all different. One might be a Chihuahua, one might be a Great Dane, and there's big differences between those instances, but there's also a lot of similarities. And so what you would say is that the essence of being a dog is the thing that all those instances have in common. And so the thing that I take away from that, I tell that story to tell this. The way that we can start to understand what does process injection mean is we can start to look at malware that fits into the category of process injection. We could look at that malware and say, that's injecting into a process. Let's see how it works, right? And we have one example of that. But we could do the same thing, and we could see a different approach, right? So this is kind of classic shellcode injection. This yellow one is what we call APC injection. And so what they did is they said, hey, typically, classic shellcode injection uses this API function called create remote thread. And a lot of defenders or a lot of EDR products or different security products started focusing on create remote thread. And so attackers were like, can we do the same thing, which is executing our code that's in memory, in a different way, a way that they don't expect us to do it? And then the way that they found it is through these things called asynchronous procedure calls. And so instead of creating a new thread, what you could do is you can say, hey, thread, you're already running, but what I want you to do is I want you to execute this thing for me. And so you just are retasking a thread, right? And there's a problem. Because if I think that process injection involves creation of a thread, I built my detections or I built my preventative controls focused on that idea, and now they've just invalidated my assumption, right? And so we have this situation to where this part of the detection or this part of the chain is the same, but this part has changed. And so it's all dependent upon how I'm trying to solve this problem. If I'm trying to solve it with the process open, maybe I'm still okay, right? If I'm trying to do it based on the allocation of memory in a remote process, maybe I'm still okay. But if I'm focused on thread create, the creation of the thread, I'm not okay anymore, right? I'm not going to detect both of these things. And so that would be a good secondary test case, right? Because now I'm taking something, I'm changing one variable. When we do testing in almost everything, what we do is we try to control all the variables and we change one at a time. And then we see what happens. If we change the one variable and we get the same result, we know that that variable is not an important component of how our solution works, right? Okay, so let's look at a third example. So this is a third example called file mapping. So if you use Cobalt Strike, for instance, Cobalt Strike has the ability to change how the code is written into memory through file mapping APIs. And so here what we see is that the process open, I think I actually have that on the next slide. Here we see process open remains the same, and in this case, thread create stays the same, right? but in this case, they've changed how the code gets written into memory. And so that's just a different focus, right? And so it's possible that we would, if we're focused on thread creation, we would still detect the same thing. But if we were focused on that memory allocation, virtual alloc EX, for instance, now they're not doing that anymore, and we would miss it, right? Okay, same thing with a fourth. Here we have atom bombing. Anybody know about atom bombing? Atom bombing was written by some guys at InSilo. Now they've been bought by some other company that I can't think of off the top of my head. But this was presented at DEF CON maybe 3-4 years ago. And the idea here is that there's these operating system objects called atoms, and they're globally accessible. And so what you could do is you could write your shellcode to that atom in the format of a string, and then you can basically create an APC just like we saw with this yellow chain, and then you would point it to the atom. So you would read the atom, which actually has code instead of a string, and then you would tell the APC to execute it. And so what we see, similarly, if I get that to work, is here there is literally no overlap between our initial example and our new atom bombing example. And so it would literally be impossible to write a detection that detects both classic shellcode injection and atom bombing, right? And this type of analysis allows us to understand that. And then the last, but here we see that this APC injection and atom bombing both share the APC create operation. That would allow us to have a overlapping detection in that case. Okay. And then the last example, this one's kind of a little bit of an old school one. I actually did some research into the history of process injection. And this last one actually came about, it's kind of a fun story. It came about from game hacking. And so one of the problems that game hackers run into is when you're trying to, like, let's say you're trying to make an aimbot for Call of Duty or something like that, the problem is you have to constantly read memory. And if you're trying to read the memory from process A to process B, you have to make a lot of external memory reads, and those are very expensive. And so what game hackers do is they inject their code into the game, and then they do local reads. And local reads are much, much quicker. And so this is an example of, as InfoSec professionals, we kind of benefit from the game hacking community, where this is not organic to InfoSec. It was something that was created by somebody completely different that had a completely different use case, but it still kind of works within the context of InfoSec. So in this case, we see that there's process open, memory allocate, process write, but then we see they go a completely different way. And they go the direction of hijacking an existing thread. So there's kind of two major kind of like subcategories. There's like the type of injection where you create a new thread, and then there's the type of injection where you hijack or take over an existing thread and redirect it, right? And in this case, we see they open a handle to a thread, suspend it, then they read the context, like all the CPU registers to see where execution is and things like that. They redirect it to the code that's been allocated, and then they resume the thread and it executes your code for you. So similar type of analysis. Here we see that all of this is the same. So this first box is going to be the same for all three approaches. But then we see down here, thread open is different than the first approach, but it's the same in these two. And then here, this is all new and unique, right? And so that just gives us this idea of, as we start to design the types of test cases we have, maybe it's useful to try out mini dump and sharp dump, because it is useful to understand whether or not your detection rule or your preventative control is built to focus on a specific tool or on a class of techniques or a class of implementations, right? And so if I detect out mini dump and then all I did was change the language from PowerShell to C# and I don't detect it, that's not a good sign, right? I should be able to detect both if it's a behavioral detection, right? But then beyond that, now we need to start looking for large variations in form, right? And so what we could say is that the biggest variation in form is this atom bombing, right? Because it shares no common operations. But maybe what we would say is, let's say I start with this one as my first test, my second test might be something like this thread hijacking, because thread hijacking is saying we're going to inject without creating a new thread. What we're going to do instead is we're going to hijack an existing thread. That's a different class. It's a different approach. And then maybe what we might do is say, okay, well, here we're using virtual alloc EX or memory allocate, process write process memory. Maybe what we're going to do instead is we're going to do this file mapping approach to where we change that variable and see what happens, right? And so we're starting to kind of triangulate what's going on here. Okay? So there's this question of like, why do attackers change tools? Why do they use different tools? Why not just use the same tool all the time? And where do these variations actually come from? I just talked about how like the game hacking community came up with a variation and then attackers read that on some blog post and they started using it. That's one way. But the other way is that it actually follows kind of like an evolutionary life cycle. So imagine like we're familiar with the idea of evolution. There's iterative change over time, right? And we understand that there's this idea called natural selection. And there's different pressures in the environment and through predation, for instance, that would cause certain things to change over time. So the environment, for instance, like I'm kind of a hairy guy. And so like my ancestors came from a cold climate, and that's why I have more body hair than somebody who doesn't, right? That's generally the idea. I don't know if that's literally what happened with me. Maybe I just got, that gene, who knows? But the idea is that your environment makes certain changes more likely to occur, right? Now imagine that in the cyber world, that's the biological world that we're talking about, but in the cyber world, your operating system is the environment. So there's certain things that the operating system is going to dictate are more likely to happen because of certain controls or certain settings and configurations that are built in. Now, there's also predation, right? So there's this great book called The Fruit, the Tree, and the Serpent, which talks about this idea called snake detection hypothesis. And the idea is that human beings developed our visual perception as a result of snakes being our primary predator over the ages. And so the idea was that all of our ancestors who couldn't see well didn't see the snake and they ended up getting eaten, right? And all the ones who could see well enough to see the snake, they survived. And so humans actually have quite developed eyesight relative to a lot of other mammals. And so the idea is that your predators are going to cause you to have some sort of change. And so in this case, from the attacker's perspective, the predator is your EDR system, is your detective controls, your preventative controls. And so we can actually, the question is which variations are most likely, right? And the answer to that question is, it depends on the selective pressure that's being applied, right? If, for instance, I build a signature where I'm looking for the word mimikatz, the most likely outcome is that somebody's going to replace cats with dogs. So we've all seen people say, I just changed mimikatz to mimi dogs, and now I got to pass the detection, right? However, if I build a detection focused on create remote thread, the API function, the most likely change is that I'm going to make a direct syscall instead of the high-level API call, right? It's predictable. If, on the other hand, I focus on the idea of detecting thread creation in the abstract, right? So it doesn't matter if you call create remote thread or nt create thread ex. It doesn't matter. I'm just looking for thread creation. Then what the attacker is going to do is they're going to find a way to execute their code without creating a thread. It's all predictable. So we can start to understand how are defenders trying to resolve this problem, and what are the likely outcomes that attackers are going to implement. And so there's this idea called the minimal stimulus necessary principle. So the idea, this is actually an idea that I stole from like bodybuilding. I'm not exactly like the bodybuilder type, but the idea is that you don't want to give somebody who's just starting out and working out, you don't want to give them like 500 pounds to squat. You want to give them something that is just enough to put them under stress so that they develop, but not enough to where they can't work out the next day, right? You want to give them the ability to continue working out so that they can get bigger over time. And the idea is that you just need to give them just enough. And I do a lot of language learning, and one of the things that you try to do is you try to give people, you try to give them input that is comprehensible. So you want to give them input that they're able to understand. You don't want to throw them, I'm learning Italian, so we got some Italians in the front row. You don't want to throw them at Dante's Inferno, right? Or in English, you don't want to throw them at Shakespeare, because Shakespeare is just like, I can't read Shakespeare. I've been speaking English my entire life, right? And so you don't want to send somebody who's just started out into Shakespeare. You want to give them something that's comprehensible. So in Italian, I started off with goosebumps, piccoli brividi, yeah. And that was like, it's kind of a kid's book, but it's a little bit, it's a little bit more comprehensible. All right, okay. So this gets back to just this idea that what we want to do is, as we change things, we want to change the bigger variables before we change the lower variables. So you all probably have seen a scale like this. If you're younger, maybe you just see digital scales. You don't know how this works. But the idea is that there's a big weight, and the big weight has increments of 25. So each line would be 25 pounds. And then you have the small weight, which would be in like grams or whatever the measurement is. And the idea is, you don't change this one first. You change this one. You make maximal change first. And then you see, okay, I'm going to change 25 pounds, 50 pounds, 75 pounds, 100 pounds. and then the thing tips over, and you're like, okay, I need to back off one, and then what I'm going to do is I'm going to start making micro adjustments. And so that's the idea of what we're doing here. We want to take those procedures or those operation chains that are maximally different. Atom bombing is very different from classic shellcode injection, and we want to test those. And the idea is that if a single detection detects, two maximally different operations or approaches, then what we're going to say is that that's a relatively robust detection, right? All right, and so what we end up with is something that's going to look like this. As we build out our test cases, we're going to make bigger changes as opposed to having all the numbers kind of stacked up in the middle, right? Okay, so hopefully this just kind of got people kind of their interest sparked, right? If you're interested in digging into this more, maybe you're interested in how I came up with those like kind of bubble graphs and all that kind of stuff. I have a blog series called On Detection that's like seven blogs long right now. It's pretty dense, I would say. I think somebody printed it out and it was like this thick, so it'll take some time. But that's free and available, so that's just something you could read about. You could understand from kind of the very highest level all the way down to some of the more technical details. I also have a workshop that's now available online. We did this at NorthSec, which is in Montreal, Canada, and that's available at this GitHub page. And there's also the YouTube video associated with it. So all the labs are available for you on GitHub, and the slides, I believe, but also the video so you can kind of listen to us talk about it. At SpecterOps, we also have a training class, which is a 4-day training class that focuses on how do I actually dig into all these different things, right? So we give me a tool and show me how to dig in so that I can actually understand what it means to create a golden ticket, right? It's not useful if I just hear the word golden ticket. I need to know how it works. And generally speaking, you need a methodology to be able to dig into that. And then we also have a Purple Team service, which is basically when we come in and work with our customers to actually run through this evaluation to help you understand where are you strong, what is the efficacy of your security controls, and how can we improve them. And then lastly, we have some sort of kind of like program development in general, which is where we just help you fix things in the abstract. So it's a little bit more open-ended than just a individual assessment. So what we're trying to do is trying to give different resources to different people at different places in their kind of journey. All I did on this slide was highlight Purple Team service because I'll talk about that a little bit. So when we start talking about the Purple Team, one question that might come up is, why don't I just use something like Atomic Red Team, right? Because ultimately what we're doing is we're doing that dynamic approach, right? We're going to run test cases and we're going to evaluate what the results are. The major differentiator is that we have very deliberate test case selection. So the test cases that we have, like I talked about with kind of these open source models, it's just quantity over quality. And that's not saying that it's bad, right? It's a good place to start. But you're not maximizing the difference. You're not maximizing the efficiency of that approach. And so what we're doing is we're explicitly choosing different test cases because they stimulate different evaluation criteria. This allows us to do something like triangulate the actual approximation of how well. There's this big question of like, we all know about like heat mapping on MITRE ATT&CK, right? Everybody's probably seen, like I try to credential dumping from LSASS, access token manipulation. Oh, we're green, we're yellow, we're red, whatever. That's all a guess, right? But you want to make that guess or that approximation with as much data to support it as possible. And this testing using these test cases, when you select them deliberately, you're making a pretty educated guess as a result. Okay. We also have, we're also evaluating your security controls across kind of 3 different components. So preventative controls, did you stop the thing from happening in the first place? Detection controls, which is, did you raise an alarm as a result of this behavior occurring? And perception, which is, do you have the raw resources in order to resolve this problem yourself? So let's say that you don't prevent it, you don't detect it. You may have telemetry through your EDR that would allow you to do that, but maybe you're just not using it, to its fullest capability. And so we help to point that out. We help to give some strategies on that. We also try to educate. So our goal is to leave you with the ability to do this on your own in the future, right? So we have this idea of, we don't want you to just think of golden tickets as golden tickets. We don't want you to think of Kerber roasting as just a word that we told you you're good or you're not good. What we want to do is we want to leave you with an understanding of what Kerber roasting is, how it works, what are the technologies involved, and what are the variables that attackers can change that will potentially invalidate your assumptions that are built into your controls. And then I think this is the last one. And then the last thing that we want to do is help model how to improve your solutions. So again, we're back with 2 of the different variations of process injection. And the way that I think about this, and I talk about this way more depth at the malware morphology workshop that I linked to. When you build a detection, you could build a detection for any of these operations, but only one at a time, right? So you could either do a process open. If you're familiar with Sysmon, that would be like a Sysmon event ID 10. Or you could do a memory allocate, process writes, something like Defender for Endpoint would have process write, for instance, or thread create. Technically speaking, thread creates the best operation to build your detection on in this case. Okay? And like I said, in the malware morphology workshop, I explained it in more detail. I'm happy to talk after this as well. But when we look at APC create, the APC creation is technically the best operation to build your detection on. But there's a problem. Those optimal operations are not shared across the 2 variations. So what do? Well, if you want to build a detection that detects both of these operational chains, the answer is you have to back off to the next best option, which is process writes. And so one of the big problems is that your detection for both variations can only be worse than your detection for each individual variation. And so what we try to do is we help to model this out, and we help to say these classes of variations, they work together. You can build a detection that would cover both of those, but for this other class of variations, you're going to need a completely different detection to be able to do that, or you're going to have to address it in a completely different way. Otherwise, you're going to lose specificity. So eventually, you're going to have more false positives as a result, or more false negatives as a result. So more error.